Barangay Guinsaogon was a vibrant farming community in the central Philippines, home to over 1,800 residents. The village sat on a fertile plain at the foot of Mount Canabag, a steep green ridge rising 700 meters above the valley floor. In early February 2006, a severe La Niña weather pattern funneled unrelenting rain across the province. In just 10 days, local stations recorded over 680 millimeters of precipitation, more than 4 times the monthly average. The resulting floods prompted municipal authorities to issue precautionary evacuation orders. By February 15th, the rain finally tapered off. As the sun peeked through the clouds, many families believed the danger had passed. Families returned home to clean their houses and sent their children back to the local elementary school. At exactly 10:20 a.m. on the morning of February 17th, the massive western face of Mount Canabag sheared away. In under 90 seconds, 20 million cubic meters of pulverized rock roared across the valley at motorway speeds, burying the entire community. This event breaks the standard understanding of natural disasters. Landslides are expected to occur while the rain is falling, not on a clear, sunny morning days after the storm has ended. The scale of the disaster was absolute. As this aerial view shows, a 3.2 square kilometer desert of dark boulders and mud instantly replaced the lush valley, reaching depths of 30 meters. The avalanche accelerated to 125 kilometers per hour. At this velocity, anyone within the direct path of the debris front had no physical possibility of evacuating on foot. Rescue efforts were hampered by the composition of the debris itself. The highly saturated mud acted like quicksand, swallowing heavy machinery and forcing responders to use bamboo poles and hand shovels to navigate the quagmire. In mere minutes, 1,126 lives were lost. Understanding why this happened requires a forensic deconstruction of the mountain's internal structure to identify the invisible triggers that wait for the rain to stop. Mount Canabag sits directly along the active Philippine fault zone, a 1,200-kilometer tectonic system that defines the region's deep geological instability. Millennia of seismic motion had shattered the mountain's internal bedrock into heavily fractured volcanic rock and sheared clay. This unstable mass was perched at a slope angle exceeding 45 degrees, held in place by a precarious balance of friction and gravity. In the days following the collapse, intense public debate centered on human responsibility. Many reports initially alleged that illegal logging and commercial deforestation had stripped the mountain of tree roots, destabilizing the slope. However, geological investigations refuted this. Tree roots only penetrate a few meters into the topsoil. This failure occurred along a deep shear plain seated 50 to 100 meters in solid bedrock, far beyond the mechanical reach of any forest network. Human surface activity was irrelevant to the collapse. Guinsaogon sat beneath a naturally occurring geological trap, primed for failure by forces deep beneath the forest floor. The mechanism behind this delayed failure is hydrogeological time lag. Even as the surface dried, millions of gallons of water were still percolating deep into the mountain's internal fractures. Because groundwater moves slowly through dense clay and fractured rock, peak pressure often occurs days after the surface rain has stopped. Groundwater is incompressible. As it filled the vertical fractures, it generated immense hydrostatic head, creating outward pressure that physically pushed the massive rock walls apart. This internal water pressure reduced the mountain's internal friction to near zero. By the morning of February 17th, the massive rock face was balancing on a pressurized fluid layer. At 10:17 a.m., a microscopic magnitude 2.6 earthquake struck along the fault. While barely felt by humans, this minor seismic shock provided the instantaneous trigger that sheared the mountain's final structural anchor. The combination of delayed deep water saturation and a tiny seismic shock caused instantaneous liquefaction. The mountain mass disintegrated during its 700-meter plunge. After 7 days of digging through impenetrable clay, official rescue operations were terminated. The municipal council designated the entire 3.2 square kilometer debris field as a sacred mass burial ground. Surviving residents were permanently relocated to New Guinsaogon, a resettlement site constructed kilometers away on geologically stable bedrock. The tragedy forced a hard-learned lesson. Survival in these regions requires aligning human settlements with geological realities rather than surface conditions. This risk is global. The Philippine Fault Zone and similar mountain systems worldwide remain highly populated and vulnerable to deep-seated landslides. Climate change is increasing the intensity of extreme precipitation, which accelerates the dangerous loading of groundwater in these fractured fault zones. Avoiding another Gonsalgan requires moving beyond surface weather forecasts. We must now deploy advanced subsurface monitoring technology, automated sensors, and satellite radar to measure the internal movements of the mountains themselves. Gonsalgan serves as a warning that clear skies can be deceiving. Preventing the next disaster requires measuring the invisible forces building beneath our feet, long before the ground begins to move.